Exercise 12.5 is asking how you would convert one pentene into a geminal dibromide. That's a molecule that has two bromines on the same carbon. So let's just draw those out first. One pentene, let's see, we'd have one, the prefix is pent, that means we have 5 carbons, so 1, 2, 3, 4, and 5. So there's our 5 carbons. We could number those. 1, 2, 3, 4, and 5. And the infix is En. That means we know we have a double bond where it starts on carbon number 1. So we have a pi bond between carbon 1 and then going to the next carbon, carbon number 2. So there's our pi bond. That's one pentene. Now we want to turn that into a geminal dibromide. Well, the easiest thing to do, they don't give us any information beyond that, so we could change it however we wanted, but the easiest thing to do would be to change as little as possible. So we keep the same number of carbons. Now a geminal dibromide, there are 2 ways that we can do this. You'll want to keep the bromines on one of the carbons that already have the reactivity on them, right? Otherwise we have to walk the electrons all over. So if we keep the bromines on one of these 2 carbons, we could either have the 2 bromines on the end or the 2 bromines in the carbon in the double bond in the middle. So on one of these 2 carbons. And the fact that the bromines are on the same carbon, that is what makes these geminal dibromides. Okay, well, let's try to get both of these just for practice. Let's see if we can get both of them, if we can make both of them from one pentene. Technically, to answer this, you would just need one of them. Now, we have learned how to make these, but it was from alkynes. So if you sort of do a retrosynthesis, you could say, I could make this if I had an alkyne, if I had not these 2 leaving groups, but if I had this terminal alkyne. Now, we'll want to make that linear. Oops. So I want to make that linear, but if you had an alkyne, then you could make both of these. After all you'd have to do is add 2 H's and 2 Brs. In other words, all you'd have to do is add excess HBr. I put these in the wrong place. The other carbon in the double bond should be there. So those are your 2 possibilities. Add excess HBr. Now if you want the hydrogens to add on the less substituted carbon, that's Markovnikov addition, and you would just need the HBr. If you want the hydrogens to add on the more substituted carbon, that's anti-Markovnikov addition. You just want to make sure you mix in peroxides there, so you can do the radical reaction. That gives you anti-Markovnikov addition. So we know that we can make those molecules out of alkynes. That's where we would have seen, that's the context that we would have seen geminal dihalides in before. But here we have an alkene. And so the question is, how can we turn this alkene into an alkyne? And we've seen the answer to that already. And this won't be the last time that we see it. It's a really useful reaction. It's a 2-step procedure. The first thing we want to do, is add Br2. Because what that'll do, first of all, if you look at this alkene, you have a pi bond, and the only thing you can do with that is an addition reaction, so you have to add something. But if you're trying to turn it into an alkyne, whatever you add has to come off. So you should add good leaving groups. It's worthwhile adding 2 bromines instead of like an HBr, because each bromine can act as a leaving group, and each elimination reaction gives you 1 pi bond. So 1 bromine leaving will give you 1 pi bond, the other bromine leaving would give you the other pi bond. And so you'd want to add Br2 instead of HBr when you're turning an alkene into an alkyne. Then, To turn this into the alkyne, it's just a two-step procedure. First, add an excess strong base like sodium amide. That will rip off both of these leaving groups. Technically, it will rip off the hydrogens next door to each of them, and those will kick off the leaving groups. The only thing is, if that's all you added, then they would also rip off the hydrogen of the terminal alkyne and make it unstable. So to stabilize that, we do a proton transfer from water in a second step. And once you have this molecule, notice they're the same, you can either use excess HBr to get a geminal dibromide on the more substituted carbon, or excess HBr and peroxide to get a geminal dibromide on the less substituted carbon. So you sort of have two possibilities here, two syntheses open to you, depending on what type of geminal dibromide you want to make. You could either start with one pentene and add first Br2 to get this dihalide, from which you can make an alkyne using first excess sodium amide, but because that would rip off the terminal hydrogen, you have to stabilize that with a water wash after it does the eliminations. And so these three steps will be the same in both of these possibilities. What's different is the last step. If you want a geminal dihalide on the more substituted carbon, then just add excess HBr, and that will do a Markovnikov addition. If you want a geminal dihalide on the less substituted carbon, that's anti-Markovnikov addition, so you'd add excess HBr in the presence of peroxides. So both of these syntheses would be, either of these would be an acceptable synthesis for turning one pentene into a geminal dibromide. So what did we learn here? What can you take from this exercise? Because it doesn't help you very much to memorize an individual exercise. What you need to understand are the principles behind these reactions so that you can apply them to different syntheses than the ones in this homework set. Ones that use the same reactions and use the same concepts but aren't the same exact syntheses. The first thing you want to remember is how to turn an alkene into an alkyne. 3 steps. Add Br2, then excess NaNH2, and water. That's the first thing. The second thing is how to make a geminal dihalide. You have to make it from an alkyne. Another important, and you can either do it Markovnikov or anti-Markovnikov. Another important principle that we kind of saw here was that these synthesis exercises are not necessarily linear. You don't start at the beginning and work to the end. Sometimes you start at the beginning, you start at the end and you work backwards. Sometimes you even start in the middle and work both ways. Here, we saw these geminal dihalides and we said to ourselves, the only time I've seen those before are in the alkyne reactions. So we thought backwards. I know I can make them from an alkyne. And then we thought backwards again. How can I make an alkyne from an alkene? So another principle to take away from this exercise is that concept of working backwards. That's called retrosynthesis. If the starting material doesn't help you, look at the product and ignore the starting material, look and think of how you know how to make that product from anything, even if it's not the starting material. Try stuff. If you get stuck, it's okay. You'll start to see connections the more times you try stuff, but trying things is the first step. So here we turned a 1-pentene into a geminal dibromide in this multi-step synthesis.